Welcome, everyone. Welcome, welcome. Yes. Welcome. Please have a seat. We're getting started here. Any seat you want, even the ones up there. You can have one of those. Always. Always. You guys are nimble. That was faster than last time. Okay. Welcome to Austin Deep Learning. So just really quick show of hands. Whose first time is it here? Don't be shy. Okay, we have a lot more new ones here. So usually with 50-50, I think we're looking at 60%, maybe 70% new. So let me get some of the boring stuff out of the way. Who here parked in the garage in the basement downstairs? You're gonna want one of these. Keep your hands raised, even if it gets tired. Okay, hands in the air. Anyone else? Anyone else? Parked downstairs and you forgot about it. Anyone else? Okay. Street parking is free on Tuesdays, so for next time you can always take advantage of that. Yes, this is Austin Deep Learning for all the new people. We usually meet on the first Tuesday of every month, except for 2 months. And this group, there's many groups in Austin about AI, of course, and this one's mostly focused on research papers and new developments, also like commercialization. So we've definitely had quite a few startups come here and give talks. And then we're mostly like, an open discussion, so it's not necessarily a lecture. It's, we're gonna have 2 speakers today, great speakers. They want you to interrupt them. They want you to ask questions. They want you to provide insights. And we've been doing this for a long time, and it's been working really well. So lots of great networking opportunities at the end of this event as well. So today's the 178th event this group has had. Thank you. So yeah, we've been around for 9 years, since August. And we're also the largest group, so we have 4,000 members. And you can help by pushing this number to 5,000. So get your phone out and scan that QR code and click join this group. You don't have to pay anything, but you will get free knowledge. Thank you. Got some more people scanning, that's good. I'll leave this up as long as we need to, no rush. Got to get those numbers up, all right. So we're gonna do 2 talks today. So the first one's gonna be given by Jason on the HRM model. And this is a really fascinating model. So it's a really small 27 million parameter model, and it can do quite a few things. And I'll let Jason talk about that. So Jason, please come up.
Cool. All right. Neat.
And as you have questions, just raise your hand and I'll make sure you get called on, okay?
All right, cool. So this paper is a really interesting, fascinating paper, and there's some follow-up work as well. I wanted to cover kind of an overview of the technology. So if this is your first time, if you don't have a lot of experience with deep learning, this is actually a good one to go to, hopefully. So we'll see. I'm going to cover what hierarchical reasoning means, the HR of the HRM. I'll talk about deep learning and neural nets and kind of build up some of that. Feel free to ask tons of questions. I'm going to go really kind of high level. There won't be a lot of equations or anything like that, but you can ask anything specific you want. I'll talk about the ACT, the computational time, which is really interesting. Go to some results. Spoiler, HRM is a diffusion model, actually, and we'll talk about that and how that works. And I'll jump into DLMs. So hierarchical AI is like, it's really exciting, right? Because it's so natural. I mean, think about when you, everyone sort of thought about this, who's done sort of AI or robotics, how, we do really high-level things like walk to this meeting, and we don't think about, oh, I need to actuate my leg and I need to like move this hip this way. Like we've moved past that, right? As a child, we sort of figured out how to walk. And as you get older, your gait changes and the way you walk changes, and so you have to continue to learn. But you're able to do that just totally passively as you kind of go about your day thinking at a higher level. And I can't remember the author, but someone coined the term, system 1, system 2 thinking. And the idea is, system 1 is kind of your automatic, things that you have built into kind of like your rote knowledge. And system 2 is your kind of really deliberate thinking. So if you're playing chess, your leg kind of bouncing on the ground, or your breathing, or these other things are all kind of covered in system 1, or maybe someone hands you a piece of paper. But the chess game is system 2, and you're able to do both at the same time. How do you say it?
Daniel Kahneman.
Daniel Kahneman? Cool.
Kahneman,
All right.
yeah.
How do you say it?
Kahneman.
Kahneman. Okay.
Kahneman.
Wow, look at you. You're like a walking encyclopedia of psychology.
I'm a human, I promise.
You go to SF for 1 week and...
It was more than a week.
All right. So, one thing that's interesting is, are they hierarchical already? How many people have asked ChatGPT or any of these models to produce JSON? There you go, right? And that's a recursive structure. So you could argue maybe you don't even have to do anything, right? I mean, you can make a case for that. So my area is reinforcement learning, so I'll talk about how hierarchy works in that field. Typically, when you talk about hierarchical decision-making or reinforcement learning, you start with your environment. You have a state. The state goes to some kind of meta-controller. And so this thing tries to figure out what is the thing that we need to be doing right now. So for example, if a robot needs to pick up a box and put it somewhere else, it first needs to walk over to the box, and the meta-controller will figure that out. It will say, now we're in the walking state. And then what happens is the meta-controller has to take the extrinsic reward, which might be 0 until you finish the entire task, and turn it into an intrinsic reward. So it needs to create a synthetic reward where as the robot walks towards the box, it gets positive reinforcement. And so the meta-controller is responsible for sort of hallucinating these rewards and making that overall problem smooth. Same kind of things apply. Do we need to do this anymore? Can you just have a giant model do this? These are all kind of open questions that people don't know the answer to. And so there's still a lot of work to do in PhD programs all over the world. Okay, so I will go through the sort of decade of deep learning very quickly. Deep neural nets, it's a chaotic composition of functions. It's a bunch of different activations, a bunch of different nodes, all acting independently. It's total chaos. And the reason you get it to do anything at all is you have a very low learning rate. You have second-order approximators like Atom and eta grad, eta delta, et cetera. And you also scale to extraordinary degree. So if you've seen Rich Sutton's bitter lesson, he basically said, we did all these tricks to like consolidate the state space, find reflections in the state space, all of that, and we just got beat by something that could run on 10,000 GPUs. And so this ends up being that thing because it scales so well. You can do model parallelism, data parallelism, all of that. A fun fact about deep learning, it's so chaotic that how many people have ever done an ensemble model, like a random forest? Okay, cool. So random forest, you break the data up into 10 pieces, you train 10 decision trees, now you get 10 answers. And if you get 10 different answers for a question, you know that you don't know what you're doing. And if you get 10 answers that are all the same, you know you're very confident for that question. Deep learning is so chaotic, people have proved that if you just train the same model on the same data in the same order, just with a different random seed, then now you have an ensemble. and you've lost like you've created almost no bias. So these kind of give you an idea of just like what that landscape looks like, right? You can even just have one model and put the output twice, and sometimes that will work. So if you're predicting a stock price and you need the confidence bounds, sometimes you can just put 3 outputs on the model: the stock price, the stock price, and the stock price. They're all the same every single time, and you will still get a pretty good distribution. There's a dropout trick as well, but the point here is like it's controlled chaos, and the alchemists have figured it out. Autoencoders. So here's an example of a neural network where if you see the neural network here is going from left to right, the left and the right-hand side are the same. So imagine an image comes in, and you want the same exact image coming out, but it has to get sort of squeezed through that hidden layer. If you look at that, you might say, well, that seems pretty impossible to do, right? I mean, you would have so much loss. But there's this amazing trick where it gets into some of this kind of like knowledge theory, epistemology, but basically, you know, imagine different concepts, like, let's say you have 2 concepts. You have how dog-like something is and how blue-like that thing is, right? So 2 totally orthogonal concepts, and you can plot out a bunch of things on that space, right? And you add a 3rd concept, you add a 4th concept. Each time you're adding a dimension and you're making that space bigger, like higher dimensional, right? If you're willing to tolerate just a little bit of correlation, or maybe, you know, if something is dog-like, it's a little bit more cat-like, even if it doesn't want to be. If you're willing to tolerate just a little bit of error, then as the number of dimensions go up, you can fit exponentially more totally orthogonal concepts. So if you have an embedding of size 1,000, you can actually fit millions, or I think it's even billions of unique concepts. So it's like, imagine billions of unique variables. Each one has their own value in 1,000 numbers. And so that is just unfathomably powerful. And embeddings, you know, feels like they power the whole world now.
Wait, so I just want to give a quick analogy. So if you have an 8-bit number, how many combinations can you store? 256, right? Okay. So it's similar, except instead of it being binary, we're using a continuous space. And so we're able to bring in a lot of different concepts in a reduced space. And when you're doing that, you're basically doing some form of compression. So if you had to ask 2 people to do a job, would you ask the person who has a good overall idea, or would you ask the person who just memorized one instance of that happening? You would ask the first person, because they have a general overall better idea, because they've done it many times, and they may not remember every single instance of them performing the job, like, you know, fixing a car or something, but they have this deep understanding, and that's what he's talking about, what autoencoders do.
Yeah, exactly. And another nice thing about autoencoders is you don't have to pay a bunch of people to label your data set, because you're just trying to produce the same image that went in. And so there's no human in the loop. You can train this on just an unbelievable amount of data, and it's just a matter of how much compute you have.
Question in the back?
Oh, yeah, go ahead.
If I understand you clearly, autoencoders are best suited for image data sets, is that correct?
That's a good question. You know, maybe, I would say that's true, but I wouldn't read too much into that. And so there are other methods that can do similar things with text. There's masking, and there's other ways to do it. So the concept of creating an embedding is multimodal. You can do it in video, images, text, et cetera. Yep. All right, so transformers. So here's just some analogies, some sort of metaphors to understand transformers, because I think a lot of people see this and they get scared, right? It's like there's this crazy graph, and there's multiple heads, and what is a head, and there's attention. So attention is basically you have 2 images, imagine stereo vision. And you know, you ever do this where you take your finger and kind of put it up, and it kind of like feels kind of weird, you try to focus on it and you go cross-eyed, right? Well, that's because that finger is close, and so it looks very different in your left or right eye, as opposed to, you know, that sign that's very far away. And so attention is kind of focusing on some saliency between two images. You can do self-attention, where you just say, look, I only have one image, but from a lot of data, I know that this is the salient part of the image. There's a deer in the forest or something like that. And then multi-head self-attention is where, imagine you're looking at a forest and there is a deer, but there's also a bird, but there's several different things that can catch your attention. And so you're representing all of them, because just depending on the context, one might be valuable or another might be valuable. So that's where the multi-head comes in. So to use a more concrete, or I guess less concrete, I don't know, to use another example, if you imagine the ambiguity in words. So if you say, like, I went to Apple today, or I ate at Apple today, clearly you're talking about the company. If you say I ate an apple today, you're talking about the apple. And so you'd want the attention mechanism for Apple to be able to represent both of those concepts. So the multi-head helps with that. The challenge with transformers is that it's a distribution. It's not sort of a binary, and so everything attends to everything else to some degree. And so you have an n-squared problem. And so there's a ton of work around how to deal with that, but that problem's not going to completely go away. Okay, so now we get into recurrent nets, and so now we'll start getting into the hierarchical reasoning model, which relies heavily on this. So what if you embedded your embedding, right? So this is a picture of a recurrent neural net that they've unrolled. So imagine you take your embedding, which in the beginning is just, let's say, the empty vector. You concatenate it to your inputs, and you run that through a model. And what comes out of that model is the next sort of version, let's say, of your embedding and some output. And then you kind of do this again every single time step. So now you're keeping some sort of memory, right? And you're also emitting an answer as you go about it. And so that looks like what's on the left. It turns out, if you run this 10 times, you would need 10 of those arrows that are going around the A, and that just becomes very difficult to read. So people will unroll it. And so what you see on the right-hand side is the same exact concept, but as you go from left to right, you're moving forward in time. And so that embedding on the left is contributing to the next one, so on and so forth. This sounds amazing, right? It seems like you get the embeddings, you get the encoding of the transformer, and you don't have the n-squared, but in practice, it's just very, very hard to train. So many problems.
Question?
Oh, sure. Sure.
Can you control the gradient of your encoding, or is it like basically an auto-encode? So the Riva is but in the name, but how much can you control? Because I reckon you can use this for so many, like, you can auto-populate like a lot of stuff using this, which is super cool. How much can you control?
Yeah, great question. I don't know if I mentioned this in the slide. Let me just go back a moment. No, I didn't talk. Oh, yeah, I did actually. So it depends on the loss function. So for example, you might produce an image, and you have now the input image and your produced image, your generated image. How do you know how close they are? And so if you compare, let's say, pixel by pixel, then you're going to end up with one type of embedding, an embedding that's like extremely sensitive to shift. Right? Because if I shift, now all those pixels are bad, right? If I use a loss that is based on, let's say, patches, and I do registration, now I'm going to end up with an embedding that's not quite so sensitive to shift, but it might be more sensitive to something else like color or something like that. So depending on your loss function, that's where the artistry really comes in. You'll end up with very different embeddings and to whatever purpose you might have. Does that help the question? Cool. All right, so a bunch of technology came out. I was known at Meta as the person who always dumped on RNNs and didn't believe in them. I feel like I called that one. I don't call a lot of things right. I feel like I got that one right. I also said no one would use speech to text, but I clearly got that one wrong. But this was one I got right, so I'll take credit for this one.
1-1.
Yeah, they tried for LSTMs, they tried GRUs, all these things, and I mean, it's a romantic idea. Like, we want them to work, right? But we haven't figured it out yet. Okay. Although it doesn't work, it worked in this paper. We'll talk about that. This is a really interesting idea. So it says, what if your embedding is not only, part of your function, but it's also a way to communicate? And this really hit me personally because I saw this at Argo, which was a self-driving car startup that I was a part of. We would have this perception team, and they would do amazing work. And they would figure out where the car is on the screen, and the car could be on the camera. The car could be occluded behind a wall, and they would still figure it out. And then what they passed over to us in the motion planning team was sort of a list of cars and pedestrians and where they were. And that list ends up not being sufficient to do good motion planning. So for example, there's a garbage bag. Can I run over it or not? I mean, maybe. I mean, if it's a grocery bag and it's just drifting in the wind, then you can hit it. If it's a full garbage bag, you can't. And so it just became huge Excel spreadsheets of ontologies, and it just never ended, and it felt like we just weren't making progress there. So the idea of like communicating with an embedding, remember what we talked about with the billions of unique concepts, right? That is the answer. And so this is sort of getting to that. It also touches on this problem where, how do you do the very quick, like, I need to pick up my foot so I don't fall over, decision making, along with the really strategic, how do I fly to Paris decision making? And so this touches on things that are really, really important in the industry. And so I think that's one of the reasons why it was so popular. Okay, mechanically, the way this works, you have a high level model that is frozen for 19 ticks and then runs on the 20th. And so it's running at a low cadence, right? You have a low-level model that's running every single tick. And without getting too much into details, they're effectively passing their hidden state or their embedding to each other. It's got a lot of similarities with the hierarchical reinforcement learning where a goal is considered an embedding that you're passing along to your sub-agents. They proposed this, BPTT free RNN, so I'll explain this. This is that same time series graph that we saw before, right? Where you're running through these you're running through these recurrent neural nets. And they said, look, let me just go back a bit because that other picture is better. You actually have to, when you get an error on the right-hand side, the far right-hand side, you have to back propagate that error all the way to the left. Because it could be that an embedding that you created at the beginning caused you to make a bad decision 10 steps later. And so what they say is, we're just going to forget about that. So we're just going to assume that the latest embedding caused all the error. And we're just going to clip the gradients. And they had this weird biological inspiration. I can just give a different inspiration. As you go backwards in time, things have less and less of an impact. And at some point, something is so distant that even if it was highly, highly correlated, it's just too far in the past. Like, too many things have happened. And so I think you can, kind of make a case, but it's pretty hand-wavy. If that's true, then why even use an RNN, right? So it's kind of shaky, and spoiler, it doesn't really work. A paper came out later where they took this part out and everything was fine.
Maybe they miss Markov models.
Oh, yeah, hidden Markov. Man, that's a throwback. Hidden Markov models.
Question?
Oh, yeah, go ahead. Sure, yeah, take your time.
Something like instead of having to go all the way back and God knows how long, can you use something like a trust decay where you don't really rely on so far back? That way, the impact is also lesser because you have a heavier influence in the latest.
Yeah, it's a great question. So this would be like the gamma function in Q-learning, right? Where at each time, the way the time decay works is at each time step, you're multiplying your impact by, let's say, 0.99, even though it seems like a number very close to 1, if you do that enough times, you get very quickly to 0. Yeah, I think so the reason they did this clipping is partly to avoid some of the mathematical problems and partly for an optimization reason. So if you do the time decay as you're suggesting, I think you'll fix some of those mathematical problems, but then you'll still have to spend a lot of computational time. I think that's what they would argue. But it's an interesting idea. It's definitely something to try out. Yeah.
Question?
Oh.
I think what jumped out of me there is, so first to answer that question, in the OSTM paper, it actually showed that you need this, like, so if you talk really deep RNNs, there's this thing they call the linear carousel, where it's like, you know, you say times 0.99 and 0.99 and 0.99. So reality, you actually don't, because you have these interaction curves in the middle that kind of like bubble up the gradient.
Yep.
So in some ways, we're actually doing the autocoded gradient, where it's like increasing and decreasing, but because if you clipped it, you can't explode with it, so it stays in this carousel. But then it's unstable. But if you think about the tension mechanism, the gradient back prop will change what it intends to. So it's like the early built-in gamma functions that just think are like, let me change what I'm intending to do.
Right.
And that's actually when I realized that I know there's enough research in transformers on it, because we don't really study what is the ill attention pattern, because I'm not able to do it. They look really weird. They're not what you think they will be, especially because they hold different heads in different places. But I'm thinking that actually like the next frontier of transformers and looking at that as like gamma functions, and in some ways we call it like mixture of experts. And then also just saying, like, what if you just drop out the gamma functions, because they don't actually matter for your sequence.
Yeah, right. Yeah. Oh man, there's something almost at the end of the talk that totally ties into that. I'll put a bookmark in that, but that is yeah, you're spot on. Yeah, right over the target. Okay. Okay, this part is cool. This is definitely the most important part of the paper. There's impact here. Think about like when you use diffusion models and you just set the number of iterations like 10 or 20 or 50. That's just random. Anytime you're just setting random hyperparameters, there's usually some kind of optimization, right? Especially when text to image is like such a big part. There's whole companies like foul.ai built around, you know, mainly text to image, text to video, and they're all just using 10, right, as the default. They're letting people control it, but they don't have a checkbox that says, hey, you figure it out. Right? That seems really important. How to know when to stop seems like an unsolved problem. Agents have it, reinforcement learning has had it forever, diffusion has it, and nobody really knows how to address it. This is the first paper that I know of that really dove into this. I'll never poop on deep learning, but Q learning, but it has to be done correctly. They missed the gamma, and so if you notice in their evaluation, it always takes the maximum number of iterations. Like at training, for some reason, it varies, but then when they evaluate, it always peaks at 20. Well, it's probably because there's no decay, right? So I don't understand why I think at training, it probably always hit 20, and then maybe it's like, oh, if I introduce a second bug, I'll make this work. But that seems important. I think even better would be some like beta regression or something like that. This is what Netflix and other places use to measure churn. But something has to be done to allow people to automatically know when to end. This is an even bigger problem for reasoning. It seems like if you add more iterations on, let's say, text to image, the image just gets more and more crisp. But another paper, which I'll talk about later, showed that if you do more iterations, it actually breaks. So the reasoning is somehow, like you can overthink a problem, I guess, literally, with these models. So this is something that folks should take a look at. Also, ChatGPT made this image, which is pretty awesome. It even references like Alan Turing as the analyzer. It's like so creative. All I put was Rocky Halting problem show, and it figured everything else out. It also said I was like violating copyright. I had to like misspell things. Anyways, it eventually figured it out.
Question?
Oh, yeah.
Just back on that little slide, so is a fixed number of iterations ever a good idea?
I don't think so. Yeah, I think that we should have an adaptive, we should do something like this. Yeah, I think this is just a gap. And I think that this is one of these things a year from now, all the systems will have it. Like you'll go to fal.ai and you'll just be able to check a box and they'll have it solved, but no one solved it yet. So it's an opportunity. Yeah, go ahead.
In my experience, this came out like I think 2016 or something. I tried to train these like back in the day. In my experience, it was just like extremely hard to train. And my understanding is that it's a good mechanism, but it's not like blow away that like the water because it is like the same way art is difficult to parallelize. Like it's just very difficult to parallelize because there's like this non-deterministic latency for training stuff.
Mhm.
It's not constant across the batch. But I don't remember if there was some like really fatal flaw in this aside from like the weird like fix it to 20 during test time. But again, really like lost out on hard competitive.
Yeah, so this, I don't, that's a good point. One thing I hadn't thought about was on the sort of implementation, the speed part of it. But what they use it for in this paper is like, when do you stop just looking at results? But that's a really good point. I mean, if you have, all sorts of batching and other things, then maybe it's like almost free to do another iteration, then this becomes less useful. Unless you're in reasoning, apparently, where you can think too hard, then I guess it's always useful.
Jason, 5.
Oh, sure. I'm actually good on time. So this didn't look like a reasoning agent. When you look at the way it solves a maze, you kind of think, imagine a person kind of, starting from the beginning and kind of worming their way to the end. But this looked a lot more like a diffusion model. Because before I sort of talk about that, let me just explain diffusion very briefly. Funny quote from Lenin: "The best way to control the opposition is to lead it yourself." I thought that was always very funny. So in this way, you create noise. So you make the image black and white, or you make the image noisy and grainy. But because you have the original, you know exactly how to reverse that. And so again, there's no need to have a human collect data or anything like that. And so that's super powerful, right? And so if you make an image black and white, you train the model to turn it into color. Then later on, if you give it a black and white image that has never been color, what happens? And the answer is unicorns, but sometimes it works. And so HRM is basically a diffusion model. It starts with chaos, right? Random embeddings. It learns order from the chaos. It's a little bit worse than diffusion because you're starting from just total chaos every time. In diffusion, you can kind of, add as much chaos as you want and then back it out. But it's the parallels are striking. And then really like what cemented it was this paper where they talk about all the different facets of HRM. And one thing I will say is people are now kind of poo-pooing HRM, saying that, oh, if you use a transformer, you get the same results, or oh, if you don't clip the gradients, you get the same result. But that doesn't necessarily mean they're not good ideas. You maybe just need to stack more of these. Not clipping the gradients is undoubtedly faster. Clipping the gradients is undoubtedly faster, right? So I think people kind of went too far anti this paper, and there's some balance there. And diffusion is amazing, continues to impress. I think that you've seen it for making game levels, making virtual worlds, but I think the large language diffusion models are super, super interesting and unexplored. Right now, people are literally treating a sentence as a one-dimensional picture and like placing words in the sentence. But that's not really how we think. Like imagine if you're outlining a book. You don't like replace chapter 4 with chapter 5. No, you kind of like, you're thinking high level, you're thinking creatively, randomly, but you're kind of injecting content, and that content is pushing everything else over. And so we need to have new ways to deal with sentences with diffusion. That's like another area. I think someone could easily get like a PhD in something like that. I think this paper came out a month ago. It's a open source language diffusion model. And I think you collectively, or you personally, should present this paper next time. I would love to hear about it.
A question?
Yeah, so I'm actually going to make a bombshell statement
Uh-oh.
that diffusion models are actually learned gradient descent models. And that's actually something that the original stability AI team, essentially that's their lecture to me when I was working with them. They pretty much said that if you think of diffusion, you add noise and figure out how to shift it, and therefore that's actually a gradient descent step, and that's what makes diffusion models so stable in training. Because like one thing is that we also didn't cover is, if you kind of compare it to the opposite thing, the image generation, that was GANs that have a mode collapse. Where RNNs kind of can't even form the mode in the first place, and they kind of have like a weird mode they form, just because they can't actually get there. But I think that we could see with all these diffusion models is that there's just stability in the fact that they can dynamically shift in real time, like how much error they're changing, and I think that that's why they're starting to work well. Because if you think about it, like you need so much data for a language model. Because I think that fundamentally transformers are not stable when you train them, and there's like a million tricks that we can have a discussion on. But diffusion kind of eliminates one of their big issues where now you're not spinning the dice on what did you attend to over time.
Right.
You're essentially saying like, okay, here's the thing I want to reconstruct. I'm just going to go and corrupt it and go reconstruct it. But you can redo this process any number of times. Where it's like, here's one example, now go attend. No, you got it wrong. Now run off to the next example.
Yeah. I think the other thing is transformers, like you've seen this where, ChatGPT will start off with kind of a bad premise and now it's stuck. It can't go back and really fix that. And so for high level stuff, diffusion, can do that. It can go back and edit and all of that. So I think you can imagine a future where like you use a diffusion model to outline your research paper and then you use a transformer to write it.
Question?
Yeah.
So as you were going through the deck, I popped into my head the article from the research paper from Anthropic about the owls. Anybody know? Ring a bell?
Oh, I haven't seen that one.
So Anthropic did this research, and they were having one model sending another model, and I assume it was the weights, the vectors from the last step. And it was sending in random numbers, but the first model had a propensity to like owls. First model did, and after a while, it was sending in a bunch of random numbers. The other model tended to start liking owls.
Oh.
And it was because there's like this hidden, this is what you were talking about, the hidden dimensions. You're able to encode all those dimensions into a small amount of information. But it was just sort of leaking that it liked owls. So
Interesting. Oh, I did see that paper. You're reminding me of it. Yeah.
Yeah, so
Let's go
there's
back and read
something
that.
there with something related to it. Anyway,
Yeah.
just a random thought.
Yeah, totally.
All right, there's it right there.
Yeah.
This is something I saw on Claude. It goes off on a bad premise and then says, sorry, that doesn't make sense. And then it goes on a different premise.
Ooh, nice.
Same response.
Yeah. I mean, the better thing is if it could, go back and edit it. But that's still like a huge step in the right direction. It's pretty remarkable that it can do that, really.
Yeah, what is the latest learning division models on having flexible size of the output? Or if instead of using it also, if we can them be flexible, at least that the size is as a maximum, not like a max. So what is the latest on that?
That's a good question. I think I read the Lada paper last night, but I was very tired. I don't think they deal with that at all. Now, this is part of the paper was here's our open source model, so they might not be on the bleeding edge. But yeah, I don't think anyone knows how to do that yet.
All right, please give it up for Jason. So next, Connor here is going to give our second talk for the day. This talk is not purely based off of this paper, but it's one of the more important grounding papers for this talk. So I'll give you a moment here to scan it so you can look at any of the relevant figures. Okay.
Hey everybody, my name is Connor Favreau. I'm a principal data scientist at Essential Health. As you might have inferred, this is a physics talk. Do we have any physicists in the room? Okay, well, it's okay. We'll all be physicists today. There is one chemist, so at least one chemist. So, my original background is atomic physics. As Rakshak said, we're going to be going over the paper, A Mathematical Perspective on Transformers. This paper is very long, and it encompasses a lot of other papers. And so we're not going to get lost in the math. There's a lot of math. If you didn't get it, it's totally okay. I didn't get it for, I don't know if I fully get it still, so we're all in that together. Okay, so what's in the black box? So we hear this expression a lot. I mean, you see this on CNBC sometimes, where there'll be analysts and they're like, oh, well, AI, And and so a lot of times we just sort of refer to this term for large language models. Now, I'm sure all of you are really, we're all here at a Deep Learning Journal Club. We want to know, what is this? And what can we infer about transformers beyond just that term? So you've seen this diagram, hundreds of times probably. Over there on the left, these are the standard blocks of the transformer, or the standard elements of it. First, we have the positional encodings. We won't go into that today. I did a previous talk on that I'm happy to share with you. Then we're going to get into residual layers. So, and then from there into attention kernels, feed-forward layers, layer normalizations, and then the last one, separate layer heads. We're not going to really get into that in this talk, but it's there. Okay, so large language models as interacting word particles. So what does that even mean? What does it mean that words are moving, interacting particles? Any Half-Life fans in here? Here we go. Yeah. So it's Halloween, October. So hope you like the Half-Life aesthetic. You see here, this is a 3D diagram of an example semantic space. And so, in general, with particles, we talk about space and things moving, particles moving. And so with language models, the space is semantic space. It's going to be the space of meaning. So as you're moving around the space, it'll mean different things semantically. So, for example, here we have on the left side you have Gordon Freeman, scientist. So personnel, protagonists of the story. On the right side we have alien creatures from another realm. They're all sort of together in the space. They're similar in meaning. In the middle there, you have zombie. So that's sort of bridging the gap between human and alien. And then laboratory below. So yeah, space in this case is just areas of meaning. And so we're also going to be looking at the actual movement of these particles in this space. And so movement in this case is just moving through the space. So you can see here, so this is that first embedding layer. This is what we're showing. So everything that we're going to be talking about is within this space. Now, a key element of particles is that they move in a trajectory. So they don't just pop here and then pop there. They're moving in a trajectory. Similarly here, what we're going to define out is the trajectory of particles. So that's where residual networks are going to come in. So when you talk about residual networks, and this doesn't have to be in the transformer, it could also be in other models as well. But really, when you have this residual network, what it's doing is it's grounding that initial position. So you see there on the right-hand side, in the red f, y, t, theta t, at every single step, we're going to be moving by that function. And so that function here is the transformer block. You see there nx. And so how we're defining time steps is one layer of the transformer block. So we're going to be moving this network, this residual network, grounds you from an initial position to another position. It's not like it's popping here, then popping there. Now, another aspect of these residual networks, just to note, is that computationally, it fits in with an ordinary differential equation solver. So a lot of motion of particles is defined by ordinary differential equations. And in computational packages, a lot of times they will use something known as the Euler method.
Is anyone here familiar with Brownian motion? Okay, so Brownian motion is how particles tend to move. So if you like drop some colored, glitter and you throw it in some water and you watch it like spread out, it usually follow a Brownian process. So that's based on like sampling from a continuous distribution or a normal Gaussian distribution many times.
Okay, so that brings us about space and time. The next big question is really, how are the particle dynamics being defined? So how is the motion actually happening? How do we define out that motion? And so that's really going to bring us into the actual block itself. Here's a diagram. On the left, I'm showing you two dimensions of hidden space. Just for the sake of convenience. So we have three words here: freedom brings unforeseen, ... In a transformer, we're predicting the next token. So the motion is going to involve the prediction. The consequence of the motion should lead to the prediction of this next word. What I'm showing you there, you can see x dot t. So x here is just going to be, the xi is going to be one particle. So I is referring to one of the particles or one of the words. So one of the tokens in the transformer. And so the dot is referring to time. So it's the time derivative. So it's how it changes with time, how it changes layer per layer. Now, what I'm showing you here, this is the full equation written out per one transformer block. And in this paper as well, there's a lot of literature about this. They really break it down into two separate. So in motion, you have forces. And so in the transformer, what's being defined is really two kinds of forces. The first one is going to be the one that is the most prominent, or the most, here you go, attention. And so in a physics sense, that's referring to a diffusive force. It is a particle, interparticle interaction force. So the attention kernel, it's going to be, Q times K, or Q dot, outer product of QK. And so that's going to be, that matrix is defining the interactions between the Q's and the K's. And so it's going to be, for example, here I have arrows drawn from freedom to all the other particles. And so that would be that inner particle force, represented by that attention kernel. There's one other force, the feed-forward layer. And so in this case, this force does not depend on the other particles. And so this is a convection force, also known as a heat flow force. And so this is the basis of our entire model. This is what's running. This is defining the motion throughout every single time step. Now, this paper brings up another element that wasn't really brought up in other papers, which is the question of layer normalization. what this is doing is it's taking this result from these forces, and it's going to project them onto a hypersphere. And it says a d-1 hypersphere. So what is that? Well, here it's going to be, so we have 2 dimensions. So here what we're doing is we're projecting it onto a circle. The -1 is coming from the fact that we are constraining the particles to move just on the circle. So the magnitude, the radius is fixed. So that's why it's -1. And so what this paper is saying is that layer normalization, so we have, several hundred dimensions. It's ultimately, and this is coming from the fact, so the RMS squared, that RMS squared is that distance, that Pythagorean theorem distance. Same thing there with just the radius in 2 dimension. That's what's going on, is because you're constraining it, it's removing one of the dimensions. I also have here a diagram of what's going on. The paper is a little bit sparse. Yes?
There was an article published some days ago from thinking machines, and it was about reanalyzed fine-tuning models with Roland. And one of the things that they were saying is that, as it's found before, that fine-tuning on the tension layer, yes or not, it seems that to be irrelevant. The only thing that really impacts fine-tuning the LLM is when you attack the feed forward. So since you have kind of reinterpreted what each part does,
Huh.
do you have any idea of why, or what could make a other interpretation of why these things happen, that it doesn't matter if you fine-tune the each layers?
That's really interesting. I didn't know that about Laura. So one way to think about that diffusive force is it's the drift. It's sort of like that base velocity. So one thing that I don't know that would be, I think, relevant here would be, what is the magnitude of that versus the magnitude from the attention? That would be my first question. Yeah, beyond that, I don't know if I could give you a full answer, but yeah, it's definitely an interesting question, and yeah, I wouldn't have thought that. Yeah, but basically though, you can kind of see there just the breakdown of the vector. So that y vector is the result of those forces, and once we project them out, we end up with that green arrow there, which is going to be tangent to that hypersphere. And I kind of break down there's that dot product that's going to be subtracted out, but that's just sort of how the geometry works out. You can actually prove that from, if you're familiar with Lagrange multipliers as well. Okay, so continuity and optimization. So we've been talking here about points, or in these transformers, it's matrix multiplication. So how do we go from these just spurious numbers into continuity? How do we get from here to here from just matrix multiplication? So the paper introduces a lot of notation related to something called measure theory. And I'm not going to get too much into that. I have a slide at the very end if you're interested. Measure theory is really looking at, it's really looking at the domain of measurements of volumes and, by extension, densities. And so the idea there is you have a density, you have a flow, and so we're dealing here with probability flows. So it's probability density flows. So we're extrapolating from just, scalar matrix multiplications out into flows, probability flows. And so as you propagate through each layer, you're going down a flow of probability. And here, the paper uses this broader expression, which in many ways encompasses a lot of the results. which is that transformers are flow maps between probability measures. Okay, so sort of getting beyond that notation, at the very bottom, you see there continuity equation. So with fluids, what comes in must come out. You must be able to account and then smoothly account for fluid flow from point A to point B. And so that's what this is saying. It's just, we need to smoothly be able to account for this probability flow, in to out. It doesn't say anything about conservation at that point. It's just saying, or about like energy itself, about how fast it moves, how efficiently. It's just saying, it has to be continuous across. That does bring us, though, into the question of energy and optimization. So, is it moving efficiently? And the answer is actually going to be not necessarily. So, on the left-hand side here, this is just another visualization of continuity of probability flow. So, you're moving time here. So again, time is each layer. Across time, it's smoothly changing. It's smoothly flowing from one to another continuously. On the right-hand side, this is getting into something called the Wasserstein gradient. And what this is getting at the idea of optimum probability transport. This is related to, in probability theory, there is a metric called the Wasserstein metric. And the Wasserstein metric, one way to think about it is, so probability distributions, just imagine that you have initially some kind of mound of dirt, and you want to move that mound of dirt into another mound of dirt. So you gotta, that takes energy. It takes, hopefully, efficiency. But the Wasserstein gradient is giving you the most efficient way to move from that initial mound of dirt into that other mound of dirt. And this has ties to physics with energy optimization as well. I'll just note too, one of the interesting things I found about this paper is that I was sort of, in physics you're always like conservation of energy, this actually, energy is not actually conserved here. It's the functional they give isn't quite the energy. So on that topic of energy, that said, it is used, one of the more interesting aspects of this paper is that, and this is actually from a previous paper that was done, the paper, it's in the references, it's called syncformers. And what they showed is that the transformer actually isn't a Wasserstein gradient flow. It isn't set up to move, completely efficiently from one, probability distribution to another. And so what this paper does is give an alternative view. So, going back to that original transformer equation, this paper gives a simplified version right here, where they basically get rid of the key and the value, key query value matrices, just make it identity, and they replace the normalization with just n. And what they prove in the paper is that this is actually a Wasserstein gradient flow. In that syncformer paper, they do a different method, or they use a different formula for this step. And in that formula, it's a little bit, it's at the end of this presentation, but it's kind of interesting. They basically do a different normalization. So in the attention kernel, you're normalizing after you do the dot product.
Sorry, that was a little quick. So
yeah.
What isn't a Wasserstein gradient? You're saying just the native vanilla transformer is not operating that way? Is that what you're saying? Okay,
Mm-hmm.
but then what is adhering to that?
Yeah, so this simplified version is a Wasserstein gradient flow. I mean, it depends on how you define a transformer. Yeah, so basically, it's like a modified transformer.
So you said you removed the keys and the queries, or what did you remove?
Yeah, so there are certain simplifications you can do. One of them is related to the, and I don't remember all of them, but yes, one of them is that you can replace the key and query matrices with just the identity matrices. And that helps out with the symmetrization. Yeah, the original Singformer paper does a few different examples of when it is properly a gradient flow, and they do various.
So you're doing token embeddings to value lookups? Is that, you said you're using identity?
That's a good question.
Yeah.
Well, so you have to remember, like, you know, the X here. I mean, it's really just the same, you know, embedding layer.
Sure.
Like it's still the same. Yeah.
So I had the same question I asked Claude. I turned up the email as much as I could. I'm going on Ask, they gave me 5 minutes for this. So here's what it actually said. The reason is that QKV projections themselves are not derived from transfer costs, they're derived entirely from optimization objectives. And the fact that you don't consistently attend the same with the KV and Q means the KV and Q actually cause spikes throughout the whole network because they're independent.
Yeah.
That the KV and Qs are initialized as a one-to-one tensor. But let's go into that because if we go into like the domain, this comes straight from linear algebra, where if we dive into it, we go to the row space, the column space, which one of them's range, one of them's the domain. I don't remember which one. If you really think about it, there's actually no more than normal guarantees when you initialize the weights of a transformer.
Yeah.
Therefore, that whole matrix, you really can't say much about its domain, but it requires for this Wasserstein thing to be, you have to have a preservation in the domain, which means your whole network has to stay on the same domain, but because every KVQ is initialized differently, we don't have that guarantee anymore. Where as soon as you said, wait, we're just taking the KVQ, it's like, actually, yeah, that makes sense because you have one distribution that you're operating on, but the key and values interact, and then the value is like the sidecar to it. That is why it is not, because it does not try to preserve it. It's trying to hit. The super peak is distribution. Like we literally do a softmax with a single peak of a distribution, so we don't really do like true softmax when you're training these.
Yeah.
So we've actually set up transformers to not model that very task.
So I mean, I kind of want to just show you like the last slide, and kind of because it kind of gets into that. Well, yeah, let me just kind of like really quickly, like, sorry, you didn't see all the other stuff. Okay, so oh crap, sorry.
See, I'm clicking here.
There we go. So this is from this other paper called, it's related to something called a Singformer. And so here, in this paper, they don't really get into the layered normalization. They just have based on just the attention. And so what they derive in this paper, they have this notation here, and I just have the sort of final, actually no, I have it at the very top. So K1 in this paper is referring to the standard self-attention. And so what this is showing is, so the green would be the query, or the keys of the query, whichever one, you know, intertwined, and then the red would be the other, would be the key of the query. And so what they're showing is that we don't fully connect between those sets in the standard transformer. So it actually kind of gets into the actual attention kernel really has a lot of ties into, so it's like an adjacency matrix. And it really ties into graph theory.
So this is also not invertible, is what it looks like.
Yeah, actually, that's a really good point too, yeah. So if it was invertible, that actually might bring us into energy conservation.
Yeah, I think that could be a good regularizer for this.
Yeah, so what they show, what sort of the result they show is that K infinity. And so what they basically do is they do both row and column normalization. So, and they alternate between the two. So in addition to just doing that first, you know, K1, that one just, you know, first softmax, They iteration over and over again, oscillating between rows and columns. That's what the NR and the NC are. Is NR is rows, normalization of rows, NC is normalization of columns. And so what they show is that this K infinity, so it's fully connected, so full flow, full conservation. This is a Wasserstein gradient. And I'll just kind of note too that in this paper, they show that you don't have to go to infinity. You don't have to do it, to infinity. Clearly, you can't to get it to converge. They say that it typically converges after about K3 or 4. So. All right. So. Okay, 6 minutes. Okay. Yeah. So. All this to say that, on this, related to this is going to be that interaction energy. This is getting that attention kernel. And they should, so this energy, based on this Wasserstein gradient flow, the gradient of this energy, similarly to a cost function, that gradient of the cost function, energy cost function, the gradient of this interaction energy is the velocity, your velocity vector in the continuity equation. So as this probability flow fluid is moving through, the velocity is tied to that interaction energy. Okay, so that's going to bring us into, so from all this, what do we get? And here we got, sort of this playing out through our toy transformer. Freedom brings unforeseen consequences. Inside Half-Life joke. Okay, so where does this lead us? This is actually going to take us into social physics. Surprise, surprise. So particle dynamics imply cluster formation in later layers. I believe that we've done a paper previously that was looking at the fact that transformers seem to cluster into just, well, actually, I think that's a separate, never mind, that's a separate thing. But I'm gonna read this little prompt here, because it's sort of like the chef's kiss of the paper. It says, ultimately, the appearance of clusters is somewhat natural, since the transformer dynamics are a weighted average of all particles, with the weights being hardwired to perform a fast selection of particles most similar to the ith particle being queried. This causes the emergence of leaders which attract all particles in their vicinity. In the NLP interpretation, where particles represent tokens, this further elucidates the wording attention as the mechanism of intertoken attraction. And the amplitude of inner product between tokens can be seen as a measure of their semantic similarity. So again, going back to that attention kernel, that is a measure of the similarity of all the tokens with each other, the keys and queries. So we're measuring similarity. So, what this is saying is that similar particles will attract. And so that will result in them moving closer, forming clusters. And they do a full detailed analysis of this at different parameters levels with beta, the dimension, and you can see there as it from t goes to infinity. And so I'll just very quickly note that there is this metastable transition that occurs that sort of reveals itself at very high dimensions. And you can, in what this is showing there, below this threshold, there's a very high probability of of all of these words formulating into just one cluster. What is that cluster? It's your final output. It's your token. It's it's the consequences, that final word. It's whatever that output was. So it's forming a consensus to one cluster. And that brings us a little bit of Rick and Morty here. Transformers are a party of changing opinions, forming a consensus. So just imagine, your tokens are opinions, are certain, and so Evil Morty, Pickle Rick, and so really what's going on is social physics opinion dynamics. And what the paper highlights is that they kind of do this very wishy-washy. They don't really fully commit to this, but they mention this. There is a lot of connection with this. They do it in explicit derivation of when d is equal to 2, of showing that it results in something called the Kuramoto oscillator, which is a crystallographer right there, I think you know, and which is a synchronization of oscillators. And yeah, so basically so in this Krauss model, this is an opinion dynamics model. And the foundation of this model is that at each time step, each particle will check out where its neighbors are. And it'll formulate around the mean of these neighbors. So if you're out with your friends and you're like, yeah, Pickle Rick or whatever, and then they all think that too, you're gonna move closer together. If not, you're gonna move farther apart. So you're forming a consensus. That's what's going on in this model.
So LLMs are just groupthink.
Yes, exactly, exactly. And actually, and this is going to be my final slide, that brings us actually, so future directions, quantum particles, this is all non-quantum. And this is a paper, and I'm not going to get too into this. This could be like a sequel talk. But there was a paper that was done very recently on, and this actually isn't even with transformers, but it's in social physics, where they take a quantum version of the Krauss model, and they actually, this paper tests Republicans and Democrats, and that's literally what the paper does. And they show that they model opinion radicalization using quantum particles. And so, yeah, I won't get too into the specifics with this, because admittedly, I've read this paper like a few weeks ago, and I don't fully remember, but yeah, but basically the idea is, with quantum particles, you get this idea of discrete states and superpositions, and radicalization is the spreading out of these states. And so this paper sort of, measures that. This is all to say that, this paper and this body of work really gets into being able to modify different aspects of this transformer and understand what's going on. And from that, we can look at, sort of, for example, with the attention kernel, that is as we said, that's a cosine similarity. Another paper out there replaces that with an electron attraction energy. So distance, 1 over r squared. So there's a lot of opportunity from this field to really be able to modify transformers and potentially get more efficient results. Yeah, so that's all I got for you guys. Yeah.
Any questions? Okay. So we're just gonna go through another minute of announcements here, and then we will break for networking. So you're welcome to stay here for another about 20 minutes to keep networking, and then after that you can head out here into the lobby if you wanted to keep chatting. Just a friendly reminder, again, to scan this. I already did this earlier. And then we have some promos here. So there's an event tomorrow and Thursday called MLOps World Summit. I think this is our 5th or 6th time doing this annually. And you guys can go for free. So this is almost $700 normally. The code is there. So if you wanted to go check that out. If you don't have a chance to get the QR code, the promo code is just the name of the group. So if you go on MLOps World Summit, you want to buy a ticket, save a bunch of money. So I'll leave that up for a second. And then we have another one. Yeah, next time you're going to an event, just like message me, because people send me this stuff all the time. Sorry about that. You want 2 parking validations? Like. If you use this code, you don't get free food though. That's the only downside. But you could, with the savings, you could buy a really 10 nice steak dinners. Okay, we still have a couple of people scanning, and then I'll show you the next one. Keep your phones warm because we have more promos. Okay. And then I wanted to bring up Christian here. He's from Prime Intellect.
Hello. Yeah, just real quick. So, does anybody here use Prime Intellect as their GPU provider? One. Okay, cool. So we have GPUs. We also have a residency for reinforcement learning. Also have a new environment hub. It's kind of like a Hugging Face, but for reinforcement learning environments. So people make these reproducible environments so you can both evaluate agents and train models. Awesome deep learning. You can add some credits to your account for GPUs. And then, yeah, if you want to do the residency, that's the QR code. I've given out, I think, a little over $50,000 in credits to residents over the past week. Yeah, we have on the Environments Hub, basically every single benchmark or recent paper that are reproduced with these environments. And if there's one you don't see on there that you want to see, just let me know. Either you can make it or we can have someone make it. And that's it.
Thank you, Christian. Okay, so again, this is Austin Deep Learning. Just one last thing, if you like the talks today, if you like reading papers, which I'm sure you do if you came today, then just let me know if there's a paper that really caught your eye and you wanted to give a talk on. You don't need to be the author or anything, but if you are, that's even better. Or if you're a startup or you're doing something really innovative and groundbreaking, maybe applying AI to a new business problem or to some underserved area, then let me know. I think those talks are also really compelling to show people where the industry is headed. And finally, thanks to Capital Factory for hosting us in this wonderful space. So now we will break for networking, so you can keep hanging out here for 20 minutes. You'll be surprised with who you'll meet, and then we'll just break out into the lobby. Thank you.